Okay, so let's start. So our next speaker is Professor Hao-Chung from National Taiwan University. So he is going to talk about error exponents of quantum computation and the entanglement distillation. So let's welcome Professor Cheng.
Okay, thanks, Professor Lin, for the nice introduction. Thanks, Professor Xie, for inviting me to give this talk, and thanks, Director Ho, to organize this very nice workshop. So this is Hao-Chung from the Electrical Engineering Department, National Taiwan University. I'm also jointly affiliated with the NCTS Physics and Math divisions. So today I will be talking about our recent work on error exponent of quantum communication and entanglement distillation. This is a work I've been working for some time, and finally we got some result I'm happy with. So this work is already on arXiv with a different name, titled Any-shot quantum decoupling, jointly with my collaborator Mario Berta at RWTH Aachen University and his former PhD postdoc. Okay, so let me start. So this is the future roadmap of quantum information technology in my head. So we'll have some local device, local quantum device. It's in the lab. It's well controlled. It's robust. Yeah, it has large qubits, large connectivity, high fidelity. You can use it to do some specific computational tasks, and hopefully we'll have some computational advantage and to do some computational quantum information, computational technology. Okay. And maybe you have seen this local device in, for example, IBM New York, and probably we'll have another local device in IBM Zurich, and maybe they have the same scales. Maybe some device is more powerful, some device is less powerful, but both I assume they are in control. They are well in control. Otherwise, we cannot have any. Probably we don't have any real quantum advantage. Okay. But in the future, sometimes we want to also have some quantum connection, quantum communication, entanglement shared between different locally geographically separated devices. We want some entanglement because classical communication just doesn't work. Okay, so suppose that this local device is very powerful, has many qubits and high connectivity, and it prepares some quantum system, some quantum states. Say it has some like 100,000 qubits to prepare 100 qubit state, some pre-trained model, and then we want the space station to send those quantum system to another local device in Zurich, for example. So that local device can do further quantum information processing to do some testing to produce some desired result. So in this way, we need to send our quantum information from one local device to another. But here we need some entanglement, we need some quantum communication. However, in this way, there's sometimes there's always quantum noise during the way because they are out of control. We cannot build a global quantum device from New York to Zurich. It's just not possible because we don't have a large-scale classical computer from New York to Zurich. So in this way, it's definitely out of control due to photon loss, due to the environment. It's out of control. Definitely there will be some quantum noise we need to deal with. So here within our lab, I assume they are in control in the future. But even in the future, we don't have control like during the way. So there must be some quantum noise along the way. So to do that, we need some powerful algorithms or coding strategies on our local device together locally. They can do locally, and then we hope to protect our quantum information transfer along the way. So that's our future idea. However, nowadays we don't have a very robust or very large scale local devices. We only have the NISQ device. So hopefully we want the algorithm implemented at our local device to be not that difficult, to be less physically demanding algorithm to implement on our local device. So that's our a general idea. Okay. So we need to talk about quantum communication and how we need to do those less demanding coding strategy on our local device to protect our data along the way. So I need to formally introduce our quantum communication protocol. Okay, So this is a more general mathematical framework of quantum communication. Say Alice at this local device, she want to send her prepared logical k-qubit state, so say like on these systems to Bob. But we have noise on the way, so we need to protect our logical qubits. So in Alice's lab, she will first encode by using her local device in control to prepare some n qubit states. So on say A1 to the AN system, those are quantum states. And then we send those quantum states to Bob's laboratory on the other side. So there's some noise. So this is corrupted or noisy n qubit states, n qubit systems. Okay, and then Bob used some decoding in his laboratory here to recover the logical k-qubit states. So that's like a general scenario. Okay, and in this picture, there are many important operational quantities we care about. For example, this n, the number of physical qubits, sometimes we call that code length or block length or code size. Example, because you at least determines how large your encoder need to prepare those systems to embed your logical qubit into a larger physical Hilbert space. So this n directly determines how large your local device need to be. Okay, and also this ratio k over n, number of logical qubits can be sent per channel use. We call this the code rate k over n. We want this rate to be as high as possible to be efficient, so that the communication to be efficient. We don't want like zero rate. Eventually, we send in zero logical qubit. We want this rate to be constant rate and also as large as possible. Okay. And also, we need to care about the error, like infidelity between your k logical qubit and your estimated or reconstructed logical qubits. So sometimes we use infidelity to measure the occurrence, and this is quite important in this work. We assume that, we want a very, very good algorithm or coding strategy such that the overall infidelity is less than some epsilon, some ratio, for example, 10 to the minus 1, 10 to the minus 3. But those three parameters are so important, and actually they are kind of the trade-off. So we need to design good algorithm to optimize them for our later application purpose. Okay, so let's get into more precise. Often we define this what we call a maximum achievable rate, which is the largest possible transmission rate among all NR epsilon code. What is the NR epsilon code? And NR epsilon code is just a pair of encoding process in Alice's lab and decoding process in Bob's lab, such that those encoder and decoder has those parameters: code length n, code rate k over n, and also infidelity no larger than epsilon. We call that NR epsilon code. So we just take to find among those possibly infinity class of codes, what's the largest R? We call it the maximum achievable rate. I put a star here. And of course, it depends. It must depend on your system size and also the error ratio. We call that the maximum achievable rate. And in literature and many papers, people consider or define channel capacity C of n as we first take n to the infinity, we find large asymptotic, large powerful codes, and we force epsilon to 0 and define this quantity as channel capacity. And this gives us a quantity or the ultimate quantity of the transferable logical qubits. So that's the physical or operational meaning for channel capacity. However, in this definition, we involve this n to the infinity. So this is an asymptotic definition. So to achieve this capacity, essentially we need arbitrarily large powerful codes, but that's very physically demanding because we need to build an infinitely large device to achieve this rate, to achieve this capacity, to achieve this ultimate quantity. Okay, so let's look at next operational quantity of interest. We call this a minimum error probability. So instead, we fix the signal size n, and we fix the number of the ratio of the logical qubit versus over physical qubits to be sent, and we find the minimal error among all possible code. We call that the minimum error probability. And in my previous work, we call that this characterizes the quality of your communication. We fix some quantity. This quantity may not be the maximum channel capacity. But this error probability gives us a hint how well in this we can do in this quantum communication. We call this quantity, this quality. Okay. Sometimes we use this error exponent to denote to give a hint that how fast the error, the quality is pretty well, how fast the error decays. This polynomial decaying or exponential decaying or what's the exponential decaying rate. We call this error exponent. Okay. In this talk, I would like to focus on another, I think, very important quantity we call the minimum colength. Instead, we fix the epsilon threshold, for example, 10 to the minus 3, and we fix the number of rate we want to send. Then, what is the minimum integer of your system size? You need to implement your code. What's the code size for your code? So we put this n star. In some literature, people call that the query complexity because we map our k qubits to the n qubits, and then how large n, then each n will go through a channel, goes through a channel. So it's like we query channel how many times. So that's a query complexity. So again, this is a quantity, this is a quality. This denotes some complexity of our for our local device to implement. So that's the general idea. I'll try to avoid some math behind, but I want to tell you why I'm interested in this question and why I think it's important. Okay, so let's look at this minimum colength complexity. Let's look at some example. For example, if we want some non-trivial error threshold better than random guessing, then if the rate is said to be capacity, and from all the known bounds, the n star diverge. We need infinitely many large device to achieve this capacity. But it's not that surprising because the definition of the channel capacity itself involves n to infinity. So this means that, this is an idealist concept. It's very nice mathematical quantity. It's very simple. It does not depend on epsilon and whatever. But to achieve this channel capacity, we need infinitely large colength. So that's not very physically nice because we don't have an infinitely large quantum device yet. So this is an asymptotic result. So this means that we need to take a rate back off a bit, not to use the full rate capacity to send. We cannot send in full rate. Okay. And if we demand the epsilon threshold to be 0, it's very demanding, and any possible rate, you can say, this n star also diverges. We cannot, in general, if your channel is noisy, like the polarizing channel with some non-trivial parameter, you cannot achieve 0 error in general for any positive rate. The n star diverge from all bounds. You can easily see this by definition. Okay, so this means that the 0 error is also demanding. We cannot really achieve 0 error. So we need to take a rate back off. We need to allow some error threshold. Not 0 is not possible, but maybe we can allow some 10 to the minus 3, 10 to the minus 5, 10 to the minus 10, for example. Then we care about how does this n star, the minimum colength or system size, scale with those parameters. So that's like the main idea. Actually, around 10 years ago, some people already realized this problem, and it's a quantum communication paper. They study this portion and they take some rate back of some delta. For example, we only want to achieve 90% of capacity, and what's the n star? So the expression is like this, is complicated, but for small error, if epsilon is small, then this rate term will dominate your performance for some constant not important right now. But this bound is not very nice because, for example, if we want to achieve 10 to the minus 3 in fidelity, then put it 1 over epsilon square, you need a million large device to achieve this rate. A million just to attain this 10 to the minus 3 error threshold. It's not very satisfying. It's very demanding for our local device. So although it's finite length, it's more practical, but it's more realistic, but it's not practical because it requires so large system size to achieve this 10 to the minus 3. If you want to achieve 10 to the minus 5, 10 to the 10, then it's almost impossible. Okay. So that's the problem in the previous work in this paper. It's a finite resource. It's very nice, but still very, very demanding. Okay. So now we know there are a trade-off between these three important quantities: the rate, the error, the colength. They characterize different quantities like this, the optimated quantity of the transmittable logical qubits. This characterizes the quality. This characterizes the complexity. If you fix, for example, if you fix code length R, then if you increase your code length, then your error will decay. Then how fast? If you fix your error, then you increase your code length, then your rate will be the transmittable rate will increase until capacity. If you fix your code length, then if you increase your code rate, your error will also increase. So it's like a trade-off between these three quantities. We want to find optimal way that our engineer or practitioner can say, oh, we want very high accuracy quantum communication 10⁻³ ratio. Then what's the size, what's the code, what's the system size we need to implement our coding strategy to protect our quantum communication. So that's a general idea. Okay. So let's see our main result in one line. So for any quantum channel, finite dimensional quantum channel, finite dimensional input, finite dimensional difference output. So we show that the minimum error is upper bounded by some constant C. That's not very important yet. So it's bounded by some quantity, some quantum communication exponent. But in here we can relax it to extract the n of for n to the n. So that's like a main result in one line. This means that the minimum error probability decays exponentially fast, not just polynomial fast, exponentially fast, and we can determine this constant, this exponential decay rate. So we call that the error exponent. And also we show that for some special examples, this error exponent is essentially asymptotic type. You cannot improve this further, and this has an analytical form. I don't want to write a mathematical definition, but we can compute this. Given your channel, given your rate, we can compute this one. And the error by using this code, also it's a random code construction, but the error decays exponentially fast. And this result tells us that, oh, we can answer the query complexity bounds. So this n star, the minimum query complexity is no larger than this guy. And this error exponent can be computed, but most importantly, the dependence on the epsilon is only logarithmic. So this gives an exponential improvement compared to the previous result. Improved from the 1 over epsilon squared to logarithmic epsilon. So if you want to achieve like 10⁻³, we just plug in then you get 3 and with some additional constant. That's also important right now. You want to achieve 10⁻⁵, 10⁻⁶, then this whole size increase a bit, several bits, but not too loud, not too bad. So that's the main point of this work, and why I'm very interested in this to derive a type analytical bound for this error exponent, so as we can answer how large system size we need to implement our code. Of course, there are still practical computational aspects, but information theoretic, I think this essentially it's now improvingly the based bound. So let's see the overall picture to summarize the previous result. So let's assume this is the code length is 1, 2 to the infinity, that the code length size. And previous results show that there are some very good one-shot bounds for n equal to 1. And a one-shot bound gives us some characterization of the transmittable rate. We can apply those one-shot bound to 2, 3, to 5, 6, for example, for n to be constant, independent of error. But in this case, the performance is actually very poor because we know that the system size must depend on your epsilon, your error epsilon. Otherwise, it's very poor. It must depend on the epsilon because we have a converse bound. So for any system size independent of the epsilon, probably very poor performance. And also, those bounds are computable by some semi-definite program, but unfortunately, semi-definite program is not efficient in the number of qubit. Because if you put it into your computer, you said, oh, your qubit size is like 20 or 30, then you'll see, oh, so slow. It takes years to compute. So those SDP are not very useful for n greater than 30, for example. Okay? But when n goes to infinity, we have very tight bound before. We call it asymptotic characterizations. That's the information theoretic limit. That's very nice, like channel capacity, but they are not realistic because it requires infinitely large system size to implement your code. And previous result, they move into a finite length from infinite asymptotic characterization to finite length. But for small error, their bound need is like 1 over epsilon squared. So it's more realistic, but still quite hard in practice. But now we are in this, I call a few length regime, and our error dependence is only logarithmic compared to a previous polynomial 1 over square terms. and we can determine this constant. We can determine everything. So it's very explicit bonds. I call that they can achieve good performance because you can make your error tolerance to be very, very small, 10 to the minus 10, and your system size not too bad. And more practical because it's not so loud. I won't say it's easy, but at least it's slightly more practical compared to previous one. And the rest question are all computational aspects, how to construct this code, how to extract this code, how to implement, how to get decomposition for those codes. So that's the general idea behind this work. Okay. So I won't go into the very mathematical details of the proof, but the main idea is we call this initial decoupling result. What's decoupling? So for example, Alice has some her system, but her system is correlated to some eavesdropper, say E. And Alice wants to do some local operation. Maybe she will rotate her system a bit and do some operation to partial trace out to show out her system. But in the end, we want that the output state is epsilon close to some product state to the eavesdropper or environment. So we call that quantum information decoupling to decouple the correlated state at the beginning to be some product state. These are already well studied in previous work, but here in this work, we studied this error criterion, this epsilon measured in terms of the relative entropy. We care about this how close, how well you can decouple your state. And often we use the random hard probing. So we put a unitary here, or we can use for example, unitary to design. We care about this how well you can decouple your system. And we obtain a tight bond, and in the NCR setting, it holds for any exponential decay. So this bond turns out to be very tight for a fidelity-based decoupling, and this is very useful for the later analysis. For example, this protocol we call quantum state merging from this famous Nature paper by Horodecki, Jonathan Oppenheim, and Andreas Winter. They studied how to transfer Alice system from one side to both sides. So essentially, this is a generalization of teleportation and entanglement swap. So let's see this picture. Alice system here, Bob's system here, and let's share some state. We assume there's a reference system to purify everything, or some Charlie, and maybe let's share some prescribed entanglement. And we allow Alice to do some local operation, Bob to do some local operation, and send some classical information from Alice to Bob. We call that one-way LCC. And after the protocol, we want Alice system to be at both sides. So essentially, it's like a teleportation. Or Alice entanglement between her system and Charlie. Now it's entangled between at both sides instead of Alice side. So we call it entanglement swap. And how much entanglement is consumed is given by conditional entropy. Okay? But then we can determine this epsilon n and the capacity ratio for this quantum state merging. Essentially, if Alice can do decoupling at her side very well, then the monogamy of entanglement and also Ullmann theorem will force those entanglement back to Bob's system. That's like a general idea already in the previous paper. Our contribution is like, this decoupling can be do very, very well, and then it's essentially tight. So our decoupling can be applied to this quantum state merging, and then quantum state merging can be used to do many tasks. For example, in this paper, essentially say, entanglement dispersion, noisy teleportation, quantum capacity, etc. We can do all of those tasks because the quantum state merging is like a model protocol for many quantum information tasks. For example, like entanglement distillation, Alice and Bob share some noisy quantum states and want some one-way LCC to distill some K bit entanglement bit. Then we can also use this quantum state merging to achieve this task to make it to achieve this exponential decay for entanglement distillation and also quantum computation. So that's like a general idea. Okay, so I don't want to go into the proof, but the mathematical proof came from my previous work with my student. We call the operator layer K theorem. It's a purely mathematical theorem. But last year, we only managed to apply this theorem to analyze some classical communication over quantum channels. But this year, we realized this theorem is actually very useful in quantum decoupling. And quantum decoupling gives us fully quantum state merging. And quantum state merging gives us entanglement distillation, gives us fully quantum communication. So kind of solve the problem like in my mind for a long time. But we go into the detail because it's a very mathematically technical. But if you are interested, please see the paper and please feel free to discuss with me. Okay, let me get into the conclusion. Now we understand the like future math. The good news is that we don't need arbitrarily large local device to implement your code. Only logarithmic in your error tolerance is enough. Then it remains to find really the explicit code construction and your circuit explicit circuit construction to achieve those good performance. So like the main message in this paper. Okay, so in summary, we obtained an error exponent, essentially tied error exponent and query complexity for initial decoupling, one-way LCD quantum state merging, entanglement, distillation, and quantum communication all in this form, and the exponent depends on your task. Okay, and so the main message is that our query complexity exponentially improves the error tolerance, error dependence from the previous work. Unfortunately, I will head to the airport soon, so I cannot, unfortunately, cannot stay for the workshop. I'll go to Seoul for another workshop. But if you have any question, please feel free to send me email about this paper. Thank you very much.
So thank you for Professor Cheng for this interesting talk. Any question? Yes, please.
Yes.
So if I understand correctly, so you prove this exponential behavior, exponential minus n to the one shot, where by using the decoupling theorem. Yeah, I would like to know more why these two are. So in the decoupling theorem, for example, is used in the Hayden-Presskill protocol, or if the applied to a black hole physics. So,
oh yes, exactly.
Yeah, and so in that case where Hall measure type maximal scrambling is necessary. Yeah,
Yes.
So I would like to know how that the decoupling theorem is related to your proof of exponential decay.
Yeah, thank you very much for a nice question. So this is a 2010 paper by Renato Renner, also Mario Berta. They also discuss quantum information decoupling. The title is called one-shot decoupling. They have some application in physics and black hole. In their paper, they use trace distance or one known, the trace known criterion in this epsilon. And they can obtain some bonds. But when they transfer their bonds to fidelity, there's a matrix loss. So their bonds are not tight enough to give our result. But in this work, our novelty is to use relative entropy, omega T relative entropy, to do decoupling and can obtain very tight bond. And this turns out, this can in turn to bond fidelity, and it's already optimal.
So that is where the decoupling, about the decoupling thing. Yeah, so, and yeah, so how is the decoupling theorem applied to the original behavior?
Yeah, so how decoupling is applied to state merging already appear in this paper, the partial quantum information paper, and also Andreas Winter's this model protocol paper, but they all use this matrix change from trace known, one known to fidelity, and they are loose. And they use some smoothing, but we don't use any entropy smoothing. So that's how we can avoid their problems. So how decoupling is used already in their paper, but our contribution is to prove this very tight relative entropy decoupling. And then we can improve all of their results. That's the whole idea.
Okay.
Thank you very much.
So, any question? Yeah, please.
Thank you for the nice talk. So I want to ask, should you define the complexity using epsilon? What if you define complexity using n, like using R? So you define n to be like the minimum with this error. Can you define n in terms of the minimum of, for example, the R or maximum? I'm not sure, maybe the maximum.
Yeah, so here our definition is to find the least integer, least system size, such that there exists some very good code and whose error is no larger than your threshold.
Yeah. So I'm thinking if you define n in terms of minimum n
Mhm.
such that R star is maybe, I'm not sure, it's less or bigger than
Mhm.
R. Could you define in
Yeah.
that way?
So
Or they're
this-
equivalent?
I think this query compressor depends on error tolerance and also the rate for any rate. So you can fix your rate at the beginning. And of course, if you have you want to achieve some rate, for example, 80% capacity, you can just plug in here.
Mhm.
And then outbound also answers the question because outbound here also depends on the rate. Here we just plug in 80% capacity in this quantity when you compute this quantity, and you also plug in your error epsilon, and you
Is that the same E1 QC as above, or
yes
you-
QC? Oh yes,
This
yes,
is the case,
there's a
okay.
QC missing here because it depends on the task. But here QC should be here in this quantum computation scenario. This N star, this E depends on the task and also depends on the rate. Here,
So
but the epsilon is separate from the protocol.
the one E superscript 1, is
Yeah.
that a definition, or it's you have some specific protocol for n equal to 1
Yes, I have some entropy quantity in this.
for one copy?
Yeah, for we call it
Single qubit.
single shot. Yes.
Okay. Okay. Thank you.
Thank you, Professor Wang.
Big on our action. So we have a couple more slides.
Yes.
Software estimate like virus load.
Yes.
So actually, a couple more slides. Where you have a bar
Oh yeah.
in the asymptotic limit, in which epsilon is n is equal to 1 over epsilon square.
Mhm.
Anyway, I think it's
The bar. Yes. Yeah.
this one, actually, this one. Yes, yes, at the limit, in the in information theoretic limit. So that estimation is actually very similar to Monte Carlo type of error estimation. Is it any related to that? So basically, it say that your error is not better than Monte Carlo, all right, in terms of code length.
Yes, but we can improve to logarithmic here.
So yours is actually not in the limit. This is actually valid for all n or n epsilon. Oh, I see. Okay, all right, got it. Thank you.
Thank you.
So due to the time limitation, we have to stop here. But if you have any question, we can stop. We can discuss it later. Okay.